Hello, welcome everyone. This is the September 14th, 2021 Open Planetary Lunch. My name is Chase. Our speaker today is Christian Tate, who is a grad student at Cornell University. He'll be talking about 3D modeling and mapping of the Perseverance rover surroundings, presenting some DTM imagery that I've been privileged to see over the last few months, and it's beautiful and exciting and neat. So thank you for being here, Christian, sharing this with us. And when you are ready, just go ahead and share your screen and start. Thank you.
Yeah, you're welcome. Yeah. All right. Okay, so I'll check. Do you see my screen? Okay, so hello. My name is Christian Tate. I'm a graduate student working with working with the Perseverance rover. I'm helping arrange some imaging campaigns. Today I want to talk to you about how using these images to map and 3D model some of the targets that we've been looking at so far. So, as you may know, the Mars 2020 mission and the Perseverance rover has of many new and improved cameras. I mainly use the Mastcam Z's. And the nav cams that are here on the mast. And but their cameras spread all throughout the rover. Yeah. And I use them all. Actually. The method that I use is called structure for motion, where you take images taken from many different branches or of many different viewpoints of the same terrain, and you reconstruct the 3D shape and color of that terrain. This has been used for over 10 years in field geology, and so on the right are my two favorite papers on the topic. And these go into more of the science and the algorithms that are used here. So I use a software called Agisoft Metashape, and this has a built-in workflow that works pretty well for the Mars Perseverance rover. And I'll jump into it. First, let me describe a little bit more about the subtleties of a structure motion. What makes a better model? So when I saw this figure from the manual, I laughed because all of these things in red circles and strikes are things that the rover does. You know, just from limitation of its operations. So the rover will drive up to a place, and it'll sit there for several days. It takes pictures mainly from that one vantage point, like like what you see up here. Actually, it is good enough to reconstruct most of the surrounding 3D terrain. So here are some of the cameras that I use, and this is just to reinforce what makes a good a structure of motion data set. We need many overlapping images. We want the resolution to be kind of on the same scale. Preferably within a factor of 4. A field of view is also important here, but that's more subtle than the resolution. Okay, so this is an example of the Daren Lee Memorial, a site that we arrived at in Sol 62, or sorry, 52 of the mission. It's so on the right you see the reconstructed terrain. And here on the left are the camera locations relative to that. So the rectangle and the line is represents the camera pointing. We have a lot of mass MZs up here, looking down on it, and some nav cams and has cams, looking from different angles. So most of what we see here is it's just from one perspective. But because we have stereo and we're looking at something pretty close, we're still able to do quite a bit of 3D structuring, even though this setup is not perfect for a structure for motion. And so here's an orthomosaic. What's a bird's eye view of the terrain. So think about it. For 2 weeks, the team sat in this location, and they looked at the rocks from one perspective, from the perspective that they could see the rocks. So up here it is an image of how they saw this rock that's in a rectangle right here. You very rarely see it in any different form. So it's useful to construct a 3D model so that you can rotate it and see it from novel perspectives, so that you're not so that you're not limited by the one view that you have seen the rocks. There are a number of other things you can do with this program and method. So a digital terrain model or a D or a DEM is taking the height of of the terrain and mapping that instead of the colors. So there are many applications for this also. For you can take the cross sections of the terrain. Say you're looking at the rocks and the height of the sand that surrounds them. You could see from this that these are the rocks, you know, right here, here, and here, 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 and here, and the level of the sand kind of follows them. Yeah. So yeah. Now, one of the challenges when you work with 3D models is how to share them. They are often large files, and it's not it's not easy to send someone a gigabyte data set and expect them to load it up and use it. So I discovered this of this website called Sketchfab. It specializes in web web presentations of 3D models. So I'll pull one up here. Here is the one we were just looking at, of the Daren Lee model. This is a slightly downsampled one for ease of web-based viewing, but it very much does the job of presenting a 3D model easily. So I could just share this link to someone, and they could bring it up on their own browser. That's very convenient for many reasons. Yeah, so. I'll go through some more examples, but first let me show what I hope to do with this. So we make I make 3D models on the 5 to 20 meter squared a scale that helps place the rover in its a geological context. And so we see where the outcrop is relative to the surrounding sands and the other outcrops around it. I've also been experimenting with more localized models that use some of the cameras that are that have much higher resolution. These have been exciting too, and I'll give some examples of this here in a few minutes. So I want to use this for exploring the site. What's around us? There are also many quantitative things we can measure, like a strike and dip. Since these models are geometrically correct, and they have scale and orientation built into them, we can make physical measurements on them. Yeah, and finally, for sorry, yeah, for education and public outreach, I haven't explored that very much, but there was some ideas for sharing this with the public, and so that they can experience what we are seeing on the surface of Mars. Yeah, and I'm not going to talk too much about constraining the camera models. That's something very close to the rest of my graduate work, but I'm not going to talk about that too much today. So I'll go through some other examples of 3D meshes and sites that I've made. This one was a little special because it on Sol 73, I started to understand how this process applied to operations, and I was able to request some images specifically to see how this would work. So I requested some wide frame mass Z's of this area to connect the engineering camera meshes with the high resolution meshes. So a mesh like this actually used all of the images we had of the area, and we were able to link one to another, all the way from the widest angle of the nav cam and front has cams down to the 110 millimeter mass cam Z's. Yeah. Yeah, so he, I love this because the resolution is so fine that you can resolve these ripples in the sand that they go throughout this model. Yeah. Here's another example of something we looked at that was about 5 meters away, and we only had high resolution on this until we took some more wide frame images to connect of the high resolution to everything else. And I'll bring up this model here because it's pretty, yeah, it's pretty spectacular that you can make a model like this from 5 meters away are you only seeing the model from this angle? I'm sorry, this angle and this angle. That's all the parallax that you have, and but this method is so versatile that you can reconstruct this with incredible detail. And of course, other regions that you can't see of the model, and there's nothing you can do about that unless you get a different perspective on the terrain. But I was very happy how this turned out. That we can make such a model from far away. So I'll just blink through a couple of other examples of workspaces, outcrops that are right in front of the rover. And these really give you as I said before, when you only see the model from one perspective, or you only see the terrain from one perspective, to have an environment where you can toggle around and see how exactly these rocks line up with those behind them, it's very valuable for targeting, getting a sense of what rocks are really unique and which ones we want to look at further. Yeah, the team has been very excited about a tool like this that presents a clean mesh like this. Yeah, so here's an example where we're looking at sand ripples actually, and these are diffuse and they don't have many features on them. Still, however, the Metashape was able to resolve their shape pretty well. So we got measurements of how high and wide these dunes are, and there's a lot of science that we're looking at for the geomorphology of how these form, evolve, and yeah. Here's another kind of example of looking at something very far away. So as I said, you went lots of different angles on a target. We've been driving perpendicular to this delta feature called Kodiak for most of the mission, from Sol 4 to Sol 130. We had this large feature off to the side, and we imaged it about a dozen times, and this parallax right here was enough to make a 3D model. And yeah, but it wasn't just the mask MZs. We also had SuperCam, which is like a telescope. It has a resolution about 5 times greater than the best other than mask MZs can do. So I took these these high resolution mask MZs and SuperCam images, and I'll put them together in a structure for motion model to make something like this, which has a lot of science in it, a lot of science. It's really spectacular. So let me load it here, just to do it justice. I have a town bus in here for scale. So this bus is here. Let me see how large the bus actually is. The bus is 14 meters long. So these layers in here are extremely important to the scientists. These circular patterns that you see right here are a flat field artifact of SuperCam. But they supply most of the resolution that you see here. But we only had SuperCam from one perspective. What that means is that we made I solved the 3D model using just the mask MZs. Then I used the aligned SuperCam images to contribute only to the texture file that's on top. So in Sketchfab, you can turn off the texture and just see this matte cap. So so this resolution is at the mask MZ high res. But we're able to take advantage of the better a SuperCam, the high resolution SuperCam images that we only have from one perspective. Yeah, so let me move on to the next example here. Since I'm talking to open planetary, I also want to mention how this other technical difficulty I found of making a mesh that has a lot of shadows in it. So beforehand, I was color processing just by making a linear stretch on the images, and of course you can't see into the shadows with a linear stretch. So at this point, I started to apply a gamma correction, so that the texture file one would have this information, and it would show the variation that's in that is in the shadow. Also, the program needs features to tie itself to in order to solve for the 3D mesh to begin with. So I found that a gamma correction really solved most of my problems there. I'm still tweaking the process of color corrections. So that's why if you look at all of these models that I have here, they all have different color spaces. You know, and it's kind of a mess. But I am getting better at pre-processing these. At pre-processing these images to make a decent texture. Yeah, so I want to finish with with this model right here, which I'm pretty proud of. Of the Mars or the Perseverance team just drilled 2 cores in this rock right here. So so what I plan on doing over the next couple of weeks is to make a model that's after each core event. So for instance, we have this right here, and I'll bring up a model that's after the abrasion event. So we abrade here to make a nice clean model, or sorry, a nice clean surface for some of the proximity instruments to work on. And the amazing thing is that some of the sand around the rock started to move, and that's something that's directly measured by this a 3D modeling method. So we can find the volume of this displaced sand here or over here. Yeah. So I've been talking for about 30 minutes so far, and I have more material, but it's okay. I would love to take questions right now if anyone has